So the next unit is just a little different. It's not that it's super hard or anything. It's just weird. So you're gonna need to take some decent notes. We're gonna review a couple things. Now this is a topic that we haven't got to in a few years because we've had to end of level review test. So I'm excited because every year the calculus teacher says to me, did you guys get to parametric equations? Because you guys use these again in calculus. And so every year I've had to say no, but this year I'll be able to say yes. So let's review a couple quick important things. Now this is really, I'm not just saying this, important going into calculus. Knowing how rationals work. And we're going to see this again today. That's why I'm bringing it up. But just as important going into next year, remembering how a rational works. You guys need to make me look good. So everybody, a rational function, I'm going to kind of scroll up so that people can in back see this graph. I'm just going to remind you of a few key features of a rational function. That means fractional function. So just a reminder, our vertical asymptote is this yellow vertical line here, and that happens where our denominator equals 0. Now think about why that makes sense. Here's my blue graph, and it's connecting through, we're trying to graph this function, and it's approaching this x value, and it can't cross it, so it's just hugging it. Does everybody see? Because can we ever divide by 0? No. So we definitely cannot be this value. So that would mean our graph would just hug it, and it would just be like, nope, can't be that, so it just goes up forever. Does that make sense, everyone? We will never ever cross a vertical asymptote because there is no way our function can be 0. Now remember, a horizontal asymptote is this tan line. It's on the horizon. Now that doesn't have to do with right here, not in the middle of the graph, but your calculus teacher is going to call it behavioral asymptote. Now that means what's happening at the very end behavior of your graphs. What value is the function approaching? Now think about it. If you remember, where this comes from is plugging in really large values for x. Because if we're talking clear on the horizon, remember we were able to figure these out by plugging in maybe like 1,000, a really big number, and calculating it and seeing what value it approaches. Does that make sense? 1,000 is not even that big. We can plug in 1,000,000. Do you guys see what I'm saying? So it came from the degrees of the polynomial on top and bottom. So we'll review that. Now horizontal asymptotes can be crossed. Just a reminder, it's just where it's approaching, so it won't matter. Even if it crosses, it'll stay right there and hug it. So it'll still be approaching that value. Everybody good? So we're doing rough sketches today. All right, let's go to this function right here. X plus 2 over x minus 3. Maybe you need to write this down, maybe you don't. This is review, but maybe you do. So if I said to you what's the vertical asymptote, you would say it's what cannot be 0. What makes the denominator 0? Sorry, makes the denominator 0? So x equals 3. So our function is going to approach 3 and then just whoop, hug it, correct? Awesome. Now our horizontal asymptote is end behavior. Let's think about this. Let's plug in 1,000,000. 1,000,000 plus 2. Will the plus 2 change much? No. What about 1,000,000 minus 3? What about the minus 3? It's not really changing much. 1,000,000 divided by 1,000,000 then is 1. Now it's not exactly 1,000,000 divided by 1,000,000. That's why it's just approaching 1. Does everybody understand that? It's getting really close to 1. So our horizontal asymptote is y equals 1. Very good. Now remember, that is because the degree on top and bottom are the same, so we would divide our leading coefficients because the millions divide out perfectly. Everybody good? Okay, let's look at this one. Vertical asymptotes. There are 2 in this case. X equals -2 I hear, and x equals 3. So there are 2 vertical asymptotes. All right, very good. Our horizontal asymptote is going to be, it's best to look at this in standard form. Now remember, it's the leading term that really matters because that's the strong thing. So when we are talking really big numbers, that's what really matters. So we have a 2x squared on top, and on bottom we'd want it in standard form so we're not mistaken. Isn't that x squared? So if we plugged in 1,000,000, wouldn't the million squareds divide out? So our horizontal asymptote will be 2. So once again, what will happen in calculus is you'll be given a like they'll ask you, they'll just give you this. They won't ask you to graph it, but they'll ask you information on the graph. So basically they'll say like, as x is approaching infinity, where's your function approaching? 2. Isn't that what the horizontal asymptote is, guys? It's an end behavior. As x is going to infinity, where's the function approaching? 2. So that's why we have to know when we get to calculus what this graph looks like in our head. Just a rough sketch. Everybody good with that? Okay, let's go to this one. Now just a reminder, it's smart on top and bottom to have it in factored form before you start deciding vertical asymptotes and even horizontal. So we have an x plus 1 on top, on bottom we have x, and then x plus 1. Don't my x plus 1s divide out? Yes. But still, x cannot be -1. Agreed? But remember, that creates not a vertical asymptote, but a A whole, good. Now that's because it still can't be, our graph still can't be an x value of -1, so it's still going to be just a graph though, but it's just like when it gets to -1, it will hurry and jump over it, but then just continue like normal. Does that make sense? Everyone remember that? Okay, so then our only vertical asymptote is x equals 0. Now my simplified function is 1 over x. So let's see what our horizontal asymptote is. Let's plug in 1,000,000. 1 divided by 1,000,000. Pretty much what? 0. One piece of bread cut up into 1,000,000 pieces. If I start spreading out the bread, there's going to be pretty much no bread there, right? It's going to be little crumbles. So it's approaching 0. So y equals 0. So that was the rule. If the degree on top is smaller than the degree on bottom, it would approach 0. So that would make sense right here, right? Both. Degree on top is smaller than the degree on bottom. Okay, very good. So you can look at the original or the simplified function. It won't matter. So if the degree on top is smaller than the degree on bottom, it would approach 0. Because if you plug in 1,000,000 right here, 1 cut into 1,000,000. Oh yeah, so now this will be our last one. Vertical asymptote, we better factor this. So on top, we factor out in, let's change colors here so we can keep them straight. We factor out an x, then left is x squared minus x minus 2. Tell me what that factors to be more, x. How do we factor quadratics? I know you know. X minus 2, x plus 1. Please, please, please tell me you can still factor. Now on bottom, we have a x plus 1, x minus 1. So my x plus 1's divide out, but still x cannot be -1. That's a whole, isn't it? Okay, awesome. So we have a vertical asymptote at x equals 1, don't we? Like this, there's a vertical asymptote at 1. My horizontal asymptote is, we can go back to the original if we like, or this one, but we'd want it in standard form. Now remember, it's really kind of, to start out, the leading terms that matter. So if we have x cubed divided by x squared, what do we get left over? X. Isn't that a linear asymptote? X to the first. Does everybody see? So remember, that was our slanted asymptote. So we went through and had to do long division to figure out what it was. If it was like x minus 2 or whatever. Does that make sense, everybody? So then on our end behaviors, it's going to approach that line, the x minus 2 or whatever it was. I'm not going to do it right now, so you'd say there's no horizontal, but there's a slanted. For right now, we're just going to say that. Everybody good? Okay. I'm not going to do this last one. I think we get the picture. Okay, let's go on to today's lesson. I just needed to remind you of that so that when we get to graphing, we don't have to push pause and review this. All right, so today's lesson, come on, I'm waiting on you. Let's go. 9-1. The reason I'm calling it 9-1, even though it's 10.6 in the book, is so that my videos are not all over the place. I know it's kind of annoying that they don't match up, but then my videos are just not all over. So it's 9-1 because we just did Unit 8. Okay, so we're getting into what are called parametric equations. So we're going to be graphing parametric equations today for the most part. So first of all, we're going to define what a plane curve is. A plane curve is like if I grabbed a flat piece of paper. This is now a three-dimensional object, right? It's a plane. It's like I can curve it, whatever. It doesn't, you know what I mean? It's just, this is a flat object, a plane. So it says, let f and g be continuous functions of t on an interval I. The set of ordered pairs f of t, g of t is a plane curve C. So f and g are going to be both continuous functions. That means there's no gaps or breaks. And they're both going to be functions of t, it says. And we're going to graph this on a certain interval of I most of the time. We're going to have a set interval where we graph on. Now it says the set of ordered pairs f of t, g of t is the plane curve C. Now where x is f of t and y is g of t. Now it says where x is f of t and y is g of t are the parametric equations for the curve C. And t is what's called a parameter. So basically, guys, we're actually just going to be graphing a bunch of x, y points, but we're going to be graphing them on an interval of time. So we're going to be graphing these. Now they're going to have meaning. We're going to start somewhere, and we're going to graph a certain way over time. So you're just going to see now there's just a parameter, which is going to be most of the time time. So it's really just plotting x, y points, though, as you will see. But it's just now it has more meaning because now it's over a certain time frame. So you'll see what I mean by this. So we've got to kind of state where we started and then where we stopped based on the time from our graph. And that's what makes it parametric. Hey. Do you need me? Oh. What makes more sense? Oh, yeah, it does. But it was still funny last night. I just thought you were giving me crap, you know?
No.
It's even more funny now. I'll have to tell you guys. Yeah.
Or is it more fun?
I thought funnier wasn't a word. What about that later? Okay, so this says graph the parametric equation on the interval from -2 to 3. So this is giving us a time frame. We're graphing on the interval from time from -2 up to 3. Now it says x is an equation of time, t squared minus 4, and y is an equation of time, t divided by 2. So how we're going to first learn how to graph these is just by making basically a t-x-y chart. So t, I would be writing this down for myself personally, x, y on my notes. So now our time frame is starting at -2 up to 3, and it's including -2 and 3, so I'll put brackets. I'm just kind of drawing myself a little picture here. X is going to be t squared minus 4, and y is going to be t divided by 2. So let's see, if we're going from a time frame starting at -2, we can graph as many points as we like. Let's just do whole numbers for this one. So -2, -1, 0, 1, 2, 3. Does everybody see how that's just our time frame here? So let's go ahead, and what we're going to do is go plug in -2 for x and figure out what our x coordinate is for time. So plug in -2 squared minus 4. 0, right, everybody? Plug in -2 here. We get -2 divided by 2, people. -1. Let's plug in -1 here. -1 squared minus 4. -3. Plug in -1. We get -1/2. So decimals are usually easier to graph. -1/2. Let's plug in 0. Don't we get -4? Plug in 0. We get 0 divided by 2 is 0. Plug in 1. We get -3. Plug in 1, we get 0.5. Plug in 2, we get 0. Are you guys with me? Okay, you act like you don't know what I'm talking about. Okay? 3 squared is 9 minus 4 is 5. And then we have 1.5. Isn't 3/2 1.5? Like I said, decimals are easier to graph. We're literally just graphing xy points now. Here's our xy points. xy, 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 xy. Now we've set these up in order from time going down, agreed? So let's go ahead, and that's what gives this meaning here. We're starting, this is our first point, we're starting at 0, 0, -1. 0, -1 is our starting point, because that was our first time. Then we're going -3 down 0.5. So now I'm going to connect those. And I'm going to put an arrow, because the time is what gives us, we're going from this point to this point next. Now let's keep going. Over -4, up 0. So I'm now connecting these with an arrow. And I'm going over -3, up 1/2. So now we're rounding around, arrow pointing. Over 0, up 1. And then we're going over 5, up 1.5. So now picture a particle moving along this plane curve. It would be starting here, and it would be like, stop. If a particle sat on there and moved around, everybody good with that? Okay. All right, pretty easy, right? Was that hard? No. Okay, then hang it through. Now, this was over an interval from -2 to 3. If they just had us graph this in general, there would just be arrows. There would just be arrows going on forever. Okay, let's do another one. Graph the parametric equation. Now we're doing on an interval from -1 to 3/2. So let's make another t-x-y chart. T-x-y chart. T is on an interval from -1 up to 1.5, because that's 3/2. And then x is 4t squared minus 4, and y is t. So this one, we could plot as many points we want. I'm not going to do a ton. Like, let's do -1, maybe 0, maybe 1, and maybe 1.5. That'll be plenty. Okay, so let's plug in -1 here for x. What did that be? 0. So then we plug in -1, we get -1. Plug in 0, we get -4. Plug in 0, we get 0. Plug in 1, we get 0, plug in 1, we get 1. Plug in 1.5, you can just do it in your calculator. I don't care if you get all fancy and do it by hand, great. But if you do that, you get 5. And then if you plug in 1.5 into t, we get 1.5. So remember, we're graphing these xy points here. So our first point is over 0 down 1. Then we're going over -4 up 0. Now let's connect them and put an arrow. Then we're going over 0 up 1. So we're coming around, arrow. And then we're going over 5 up 1.5. Does this graph look familiar? It's the exact same graph, isn't it? So I'm going to put those two graphs right next to each other that we just graphed so that you guys can just see what happened here. We had two parametric equations with different intervals of time. Now, isn't this interval of time from -2 up to 3 much longer than the interval from -1 up to 1.5? Yeah, it's a longer interval of time than this. Now, we had different parametric equations. So the graphs are the exact same, but they just happen over different time intervals. One happens much quicker than the other. Kind of making sense? Okay, cool. All right, so now you know how to graph by using a TXY chart, a parametric equation. All right, so now I'm going to teach you another way to graph, okay? This is not learning anything new. It's just instead of creating a TXY chart, we're going to learn how to graph by what's called removing the parameter. So on your notes, you should write that. That is literally what it's going to say on the test. Graph by removing the parameter. Or they might say, what we're doing is, instead of doing a TXY chart, we want to create rectangular coordinates, meaning we want to just have a regular, good old school y equals a function of x. So that's what we're going to do, is we're going to remove the parameter of t. We're going to remove the parameters of time. So once again, we know we could make a TXY chart to graph this. However, it really is easier to just graph a y equals function. We usually in math graph y equals a function, and it's usually a function of x. Agreed? If we make a normal old xy chart for ourselves. Okay, so look right here. We have y equals, and then it's 2t. We need it to not be t, but a function of x, because then it's like the good old school graphing. Does everybody see? Yeah, so we'll just do a substitution. So what we have to do is go over here and say, well, first of all, I have my x, yes, but I need to get t alone. T is what I've got to substitute in. Does everybody see? So let's use this, get t alone piece by piece using algebra. Add 4. So we have x plus 4 equals t squared. Square root, when solving and taking a square root, you can't forget you have a plus or minus. So we have plus and minus the square root of x plus 4. That's equal to t. So now what we can do is write our function, instead of with a t, with a x. Now we have a function in terms of x. So what we have is this. Y is equal to, we have 2, and then times by plus or minus the square root of x plus 4. So now, just a reminder, this is a times sign. So if you really think about it, our final answer will just be y is equal to plus or minus 2, correct? Multiply. So we would have plus or minus 2, and then the square root of x plus 4. So what I want you to do now is graph this, and I'm going to let you use your calculator. Before we couldn't really use our calculator because they weren't functions with x and y, and that's what our calculator can only do rectangular coordinates. So what you're going to do is go to y equals, I'm not going to pull up mine, I'm just going to explain to you verbally, and I'm going to kind of do a rough sketch here. So what I want you to do is go to y equals, and in y1, you would type in the positive square root. So you'll just do the square root, right here, positive square root. So you'll do 2 square root of x plus 4. Then in y2, you'll type in negative 2 square roots of x plus 4. Now you'll hit graph. And I'll do right here a rough sketch. So I'm going to come look at somebody's graph here in a second on their calculator. Thank you. Which I guess I shouldn't have even needed to, because really I could do it. Shift left 4 units, positive square root, negative square root. Good graph though. Now look, if I said to you graph, you're not allowed to give me a rough sketch. I want exact points. So now hit second y equals. Second graph, not second y equals. Hit second graph. Remember, those are the table of values. And you guys see how you have your x, y points? Okay, cool. So you just plot points. Which points would you choose to graph? Whole numbers, wouldn't you? Okay, cool. So that would be how you'd graph it. Pretty easy, right? So it's kind of nice if you remove the parameter and then graph it, because then you can just kind of type it into your calculator. Okay, we're going to do another one by removing the parameter. In other words, putting it in rectangular coordinates. All right, so this says eliminate the parameter and sketch the graph. So that means put me into y equals a function of x form. So we're going to leave this as this. We need this to be a function of x. So now we'll go over here and we got to get t alone so we can substitute it in. Now it's just basic algebra. We got to do basic algebra correctly. So let's see if our algebra skills are up to par. What should we do first? So multiply by, so you're, yes, switch t and x, but let's do let's say what we were doing mathematically. You're multiplying by, because everybody's going to see y. Multiply both sides by root t. So we have root t times x equals 1. Then what? Divide by x. Keep your goal in mind. You're trying to get t alone. So we have square root of t equals 1 over x. Square it. This is squaring, not square rooting, so there's no plus or minus. Don't get that backwards in your head. Then don't we just square that, square that? Yeah, that's not breaking a forbidden rule, right? There's no plus signs there. So that's 1 over x squared. So now we'll go and take that, plug it in wherever there's a t. So we have y is equal to 2, and then parentheses, 1 over x squared, and then that was squared. So now we'll square that, square that. So we have y is equal to 2 over 1 squared is 1, so then that would just be 1, and then x to the 4th. Now here's the thing, if you were to just type that into your calculator, you're not going to get full points because this is a rational function. This is why we reviewed what we reviewed in the beginning of our lesson. If you just graph it, it's not going to do asymptotes on your calculator, right? So let's just do all of this one by hand. It's quicker than calculator. It literally is. You would say, what is your vertical asymptote? X equals 0. It's what makes the bottom 0. So that'd be the first thing you quickly draw in. Then you could say, what's your horizontal asymptote? Plug in 1,000. 2 divided by 1,000 to the 4th. 0. Y equals 0. So that would be right here on the horizon. Now watch, even after this, still much easier just to plot. Don't we just plot a couple points and we know it's going to approach our asymptote? So let's plug in a 1. 2 divided by 1 to the 4th is 2. So we have the point over 1 up 2 units, over 1 up 2. So that's plenty, isn't it? It's going to approach this asymptote, never cross it. It's going to approach this asymptote, and who cares if it crosses it, right? Eventually? Because if it crosses it, it'll still hug it. Rough sketch. Okay, moving on. Let's plug in negative 1. 2 over negative 1 to the 4th is positive 1. So don't we get negative 1, 2 again? Negative 1 up 2 units. Well, that must mean this is approaching this asymptote, and this is approaching this asymptote. All good? Done. Okay, you guys are doing great. We're actually pretty dang close to being done with the lesson. The rest of the time we'll be here some homework here soon. Okay, sticking with me here. Come on, come on. Okay, let's quickly review how to graph circles because it's been since secondary 2. I haven't taught you this in secondary. You learned this a long time ago. Circles have the form x squared plus y squared equals radius squared. So that's true. Then right here, oh yeah, and then this has a center at 0, 0, and then r is equal to your radius, right? So this is r squared. So right here is a circle. This is the form of a circle. Now what's my center at? 0, 0, isn't it? No shift left and right, no shift up and down. My radius is not 16. That's radius squared. So our radius is 4. Does everybody see? Okay, let's go to this one. What's the center? Shifted right 3 units. It's actually down 1, so this is a 1 fluke. Usually with shifts up and down we stay the same, but because y is in parentheses, it's opposite. So 3, negative 1, and then our radius is 7. So then we just graph our circle. Now look, there is something majorly different on this last one here. What? The 6. Does everybody see? We now have this like stretch on our y kind of type thing. This is actually not creating a circle, so these are creating perfect circles. This is what's going to create more of a football shape, like an ellipse. Because it's like stretching it out in a way. Does that make sense? So it's either going to be like that or like that. I'm trying to think. I think it would be like that. I think it's going to be more like this. Now here's the thing. If I asked you to graph this, how would you graph it? These circles are easy to graph, correct? But with the ellipse, it's a little harder. So this is my opinion, personally. I'm sure your teachers probably taught this different last year. I personally don't want to get into how to graph an ellipse, so I would just go like this, but this is just me. Okay, if you can remember how to graph an ellipse your own way, great. Good for you. Do it that way then. What I would do is say, I would rather just plug this into my calculator, but I can't plug it in unless I have it to y equals. So let's get y by itself. So the first thing we would do is subtract this, wouldn't we? So then we would have 6 times y minus 3 squared equals 25 minus x plus 2 squared. Next step, get y alone, divide by 6. Now, yeah, this is ugly, but we're going to just type it into our calculator. Oh, this isn't, sorry. Okay, so then what would we do? Square root it. Wouldn't we need a plus or minus? So then what would we do after that? Add 3. So we would have this. Y is equal to plus and minus the square root of 25 minus x plus 2 squared divided by 6 plus 3. And I would just type in y1, I type in the positive, and y2, I type in the negative, and then I'd hit second y equals and get some xy points. That's just how I know how to do it quickest. I don't remember. I just need to look it up. I don't remember how to graph an ellipse otherwise. Same thing, right, though? Just a different way of graphing it. That is the same function. So you'll see that it creates a football shape. I'm curious kind of what the football shape looks like. Maybe, should we take a second and type that in real quick? Or do you not really care? I'm curious. It's been a long time. I haven't taught secondary 2 since like my first year teaching. What? Okay. Can I see it? Yeah. So it's looking like this. There's the XY chart. It's looking like this. It works.
It creates 2 separate graphs.
Yeah, it's 2 separate graphs just like before. Oh, yeah, yours worked too. See, it's creating that weird football looking shape. I don't know. So hit second y equals. I can't remember really a lot about ellipses, as you can tell. Yes. Yes. It's just there's not a hole because there's no, like, we're not dividing, right? Holes come from tops and bottoms dividing out. You don't really have a hole. It's just a fluke in your like calculator. It's like a glitch kind of type thing. No, it's not actually a hole. It does actually close. There's no reason for it to not. It's just your calculator is having a hard time graphing it perfectly. Yeah, that's probably, yeah. True, good point. Okay, you guys kind of get the picture, I feel like. Okay, moving on. We're almost done with the lesson. Literally almost done. Write this down. This one always gets to people, and I can see why. If you don't remember how to do it, sometimes I can see why you'd get stuck. So it says graph the parametric equation. So it has x is equal to 2 cosine theta, y is equal to 2 sine theta, and then it says on an interval from 0 to 2 pi. So now if you think about it, on an interval from 0 to 2 pi, since we're graphing like technically cosine and sine, we are technically graphing one cycle. Because isn't 0 to 2 pi one cycle? Now I personally do not, so what's my parameter here? Parameter on this one's not time, but it's theta. Isn't that our parameter? So if we really wanted, this is not how I'm going to do it, so don't write this down. You could make a theta and then an x, y chart, couldn't you? So then this would be 2 cosine theta, and this would be 2 sine theta, and then what would you plug in for theta? Values around the unit circle, correct? I personally just like graphing rectangular, not theta, like not cosine and sine. I'd rather just graph a rectangular function. So I'm going to remove the parameter, everybody. I'm not going to do it this way. I don't want to have to do unit circle on this one. No, you could remove the parameter. No, they're going to not ask you. You'll just remove the parameter for these ones always. So let's go ahead and say, well, what true statement do we know where we could maybe rewrite this? So first of all, just a reminder, we have a trig identity that's this. Sine squared theta plus cosine squared theta equals 1. Now what we're going to do is we're going to use this to create rectangular coordinates. So what we do know is we would rather graph something with x's and y's than sines and cosines. Personally, do you agree? X and y's are way easier to graph. So let's go ahead and go to this true statement, and let's get cosine all by itself, because then we can replace our cosine with whatever we have. So get cosine by itself. Divide by 2. So you're saying that cosine of theta is equivalent to x over 2. Yes, that's going to be nice. Get sine by itself, so divide by 2. So we also know that sine of theta is equal to y divided by 2. Now look what we can do. We can take those values and substitute them in to create rectangular coordinates instead of having trig. So we're going to take this and plug it in right there. Take this and plug it in right there, because that is sine. You guys see a new true statement. So then we have y over 2 squared plus x over 2 squared equals 1. And now do you guys see how we have rectangular coordinates to graph? Now let's simplify this. So if you recall, you'll square both of these. That would be y squared over 4 plus x squared over 4 equals 1. Now I don't want to have to do fractions, so couldn't I mathematically times everything by 4? As long as you do it to everything. So I'm going to times everything by 4. Times by 4 here and by here. So won't my 4's divide out? So now it's a circle. So y squared plus x squared equals 4, which would be better written as x squared plus y squared equals 4. So that's way easier. You would have got the same graph going around in a circle and graphing, but this was easier. So now where's your center? 0, 0. Radius is 2. So you'd say 0, 0, out 2, up 2, over 2, down 2, and that was easier. You'll convert them to rectangular most of the time.
Like in this unit, they're going to be a bunch of
Oh, yes, yes.
Why did we decide it like this?
Because we had to come up with a way to relate this to each other so that we could rewrite it with rectangular coordinates. So that was the only trig identity where sine and cosine were the only trig functions in the true statement. Does that make sense?
Yes.
Kind of? Okay, cool. All right, awesome. Okay, this is the last example of the day, and then you'll be able to get most of the homework done in class today. So let's look how easy this one is. Write the parametric equation given that y equals 1 minus x squared. So it says x equals t. Parametric equation means we have a t, an x, and a y, where t is t, and then x is a function of t, and y is a function of t. So how do we write x as a function of t? Well, it told you right there. X is t. You guys see? So we would say x equals t. Now y, for it to be parametric, is an equation that has t's in it. So couldn't we go here? Isn't this the equation? And we need to take our x equals t and plug it in there to make it back to parametric. You see how we're going from rectangular to parametric? So what would be? You'd be y equals, that's your parametric equation. Easy peasy. It's just now writing it with t instead of x. Instead of rectangular. Does that make sense, everyone? So what would this one be? T, x is equal to t minus 1, and y is equal to, wouldn't we go substitute that in? So 1 minus t minus 1 squared. And that's your parametric equation. That is the parametric equation. Those are equivalent true statements. One's rectangular, one is parametric. Now, if the back of the book has this multiplied out and combining like terms, great. That's no different than this problem, correct? Standard form and factor form are equally good. So that answer would be acceptable, but also distributing and combining like terms would be acceptable. Okay, awesome. The homework is, you have it on your paper. Look at that. That's more accurate than this up here. So I'm going to push pause, ask questions, and ready, set, go.